All right, ladies and gentlemen. Page 135, question number 1b, is a similar question to the last example that we've shown in section 3.3, except in this case, there is friction acting on mass number 1. Mass number 1 has a mass of 1.20 kilograms. Is that correct? And mass number 2, the hanging mass, has a mass of 0.60 kilograms. So let's start with this hanging mass, because this is exactly the same as in the previous example. There are two forces acting on this mass. The obvious one is gravity acting in the downward direction. We can calculate what gravity is. What's the equation for gravity? Can you remember? And if you don't remember, that's perfectly okay. Just look back to your notes. That's the important part, knowing where to find it. Zeal?
Gravity equals mass times.
Good. We call this G, the gravitational field intensity, or the acceleration due to gravity. We don't call it gravity. Gravity is the force, the F. So in this case, gravity is equal to mg. Now this is not the only force acting on this object. Just like in the previous example, there's another force acting on it. What is the other force, and in which direction, Anna?
Tension and up.
Good. So tension is acting up. Now let's look at the cart. Since the cart and the mass are connected by one rope, then there must be a force of tension pulling this as well. And I've drawn them both in red to show you that the force of tension acting on the cart is exactly the same magnitude as the force of tension pulling up on the weight. Since they're attached, the tension has to be continuous for both. Another assumption we have to make sure we make right and down positive. This is the direction of motion. The cart's going to be moving to the right and the mass is going to be moving down, both of which are drawn or pulled by the exact same acceleration. Since they're connected, their acceleration will be the same. It's going to pull the mass down, it's going to pull the cart to the right. We got that? In the question, they tell us that there's another force acting on the cart. What is that other force? What's the other force acting on the cart? And in which direction is friction going to travel? Left. So friction always opposes motion. So we have the force of friction backwards. Okay, we're going to attack this question the way we're going to be attacking all questions in this section. The very first thing we're going to do is list all of the forces acting on object number 1 and all of the forces acting on object number 2. Keeping in mind that right and down are positive, who can tell me what forces are acting on object number 1? Matt?
Tension and friction.
So we're going to add them up, keeping in mind their direction. So we're going to say tension minus friction. What about for this second one here? Down is positive, up is negative. What statement will I write for the second object?
Tension minus gravity.
Gravity is down and it's positive.
Oh, gravity minus tension.
That's right. So just like in the previous example, gravity minus tension. What's the second step? The second step is to replace the expression F net with the equation. What's the equation that we're going to be replacing it with?
M1A.
Good. So for this one, it's going to be M1A equals tension minus friction. And for this one here, it's going to be M2A equals, what can I put instead of gravity? Let's put the equation for gravity, which is m2g minus tension. The whole point of this question is to determine the acceleration of this system, of the sliding cart and the falling mass. So acceleration is present in both of these, but we need to unite them to solve for that one variable. Hopefully there's one piece of information that is the same in both equations, so that we can unite these two equations together. We've drawn the tension in red to indicate that the tension in this object is the same as the tension acting on this object. So we can actually isolate these and make them equal to each other because they are equal to each other. So solve this side for tension and solve this side for tension. If we get tension by itself over here, we're going to take this negative friction, bring it over the equal sign, so we end up with tension is equal to m1a plus the force of friction. For object 2, let's bring this negative tension over this side, because when we bring it over the equal sign, it's going to become positive. And let's take this m2a and bring it on the other side. We end up with tension is equal to m2g minus m2a. So tension equals this, and tension equals that. That must mean that this is equal to that. So we're going to say that this, m1a plus force of friction, is equal to this, m2g minus m2a. Remember that the point of this is to solve for a. So in doing so, let's get all of the a's on the same side and bring everything else on the other side. So let's take this term here, m2a, and bring it over the equal sign. Let's take this friction and bring it away because we don't need it on that side. So we end up with m1a plus m2a is equal to m2g minus force of friction. Almost done. To get this a and solve for a, we have to isolate it from each of the terms on the left-hand side. This is going to require that we use a skill that we learned in grade 10 called factoring. Let's factor an a out of this side. If you factor an a out of each term, what are you left with inside the brackets? Selena? Perfect. Okay, last step. To get a by itself, divide both sides by m1 plus m2. And we can sub and solve. The m1 and m2 cancel out on this side, and we're left with m2g minus force of friction over m1 plus m2. If you look carefully, this is almost identical to the acceleration we solved for yesterday. What's the only difference? Sam?
Subtracting friction.
We're subtracting friction. Now let's see if that makes sense. What's the one reason that this whole system is accelerating? What's driving the acceleration?
Gravity.
Good. And the term for gravity is this term right here. So gravity is going to cause it to accelerate. If there were friction, friction would cause it to accelerate more slowly. So in this case, it's showing that friction is taking away from the force of gravity, which is causing it to accelerate. See how that works? So gravity is causing it to accelerate, and friction is taking away from this acceleration. Now we divide by the masses. The acceleration is going to be bigger if the masses are smaller, and it's going to be smaller if the masses are bigger, because we're dividing by m1 plus m2. So in this equation, you actually get a lot of information about the dynamic system that we've set up. I want you to sub and solve and tell me what you get for this. Another tricky part in answering these questions is making sure you choose the right masses and the correct values for friction when you're subbing and solving. So everyone do this together with me, where we have 0.6 kilograms times 9.8 newtons per kilogram. The friction from the textbook is 0.50 newtons divided by mass 1 is 1.20 kilograms plus 0.60 kilograms. If you punch this into your calculator, you should get 3.0 newtons per kilogram. What else could I write instead of newtons per kilogram, Alex?
Meters per second.
Good, or meters per second squared. When expressing your answer, if you're talking about the cart, you have to say the direction of the acceleration is to the right. But if you're talking about the mass is not moving to the right. What direction is the mass moving? The cart moves to the right, the mass moves down.